Okay, good morning, everyone, and thanks for turning up to attend another of our Overberg Gesocientists presentation. I'd like this morning to welcome Jock Harmer to the group, and he's going to be our presenter. I think many of you will know him, but just by way of brief background, Jock graduated with an MSc, a four-year degree, and then an MSc at the University of Natal, and then moved on to UCT to do a PhD in geochemistry in 1993. Subsequent to that, he's had a varied but very illustrious career. He worked at the CSIR and then moved to the University of Pretoria and the Bushveld Institute, where he was a senior lecturer in the geology department. He then also had a stint at the Council for Geoscience, and then moved, interestingly, into junior exploration and I guess mostly exploration, but also mining companies, Pan Palladium being one, African Platinum PLC, and also involved with Impala Platinum. He's been particularly focused in recent years on carbonatites and rare earths and those sort of minerals. He's given us a talk previously on Greenland, which was most interesting. And today he's going to talk on that fascinating volcano called Oldoinyo L'engai in the East African Rift. So we really look forward to it. Thanks, Jock. Over to you.
Okay, thanks. Yeah, this talk has had the most confused title through the 4 or 5 months that we've talked about putting it on. But working in carbonatites in the period that I sort of specialized into it through the 90s, Lengai loomed fairly large in people's thinking, and it had both positive and negative influences that I'll try and bring out. So the opening picture there is a photograph I took in 1995 when we went on a trip and climbed to the top of Lengai. So it's built around it. I'm not a Lengai specialist at all, but I just think from looking at the sidelines, it's had some interesting influences. So just first off, let's have a look at where it is. There's a photograph of Lengai with its characteristic cloud on top, and its sister or brother volcano, Kirimasi, which is very, very close. Very, very similar setup. And Kirimasi was also an alkali carbonatite volcano. There's no alkali volcanics left. There is just a calcrete capping. So Oldoinyo L'engai and Kirimasi next to each other, just right on the edge of the rift scarp here. And then just some, just to locate yourself, there's the big shield volcano of Kilimanjaro and Mount Meru there. And the map on the right is quite an interesting one because it shows the two volcanoes, but then these other dots here are little cinder cones and volcanic edifices right the way through the valley floor. So it's not like there's an isolated volcano here and an isolated volcano there. When you walk around on the ground, it's really in a very, very active area. So just some history of it. It was first described or depicted on a map in 1855 and described as being snow-capped. It was recognized at the time as a volcano. It's the Lengai part of the name that translates into God in the Swahili sort of language. So it was known as a volcano prior to 1900. But the first scientific account was when Jaeger climbed to the top and had a look in, and described as having two craters, a southern extinct southern crater and active northern crater. Importantly, described it as emitting mud flows and fumarolic gases. And the being described as snow-capped is a bit controversial because the altitude is not high enough to actually have snow on it. It was listed as one of two volcanoes in the region, the other being Kilimanjaro, that had snow on top. And the whiteness that they saw on the top is in fact the alteration products of the lavas. Some examples from some more recent pictures. The lava at Lengai, when it comes out, is black, as shown in the right here. And within days, going into weeks and months, it turns white and decays away. So that's just the explanation of why it was described as snow-capped. So a lot of the initial stuff here is reliant on excellent documentations and write-ups that Barry Dawson's done and did in a couple of papers in the 60s and the 70s. On the right is from a publication of his, just detailing from 1915 through to 1988 the activity. Now, if you have a look at the sections, you'll see in the 1915 one, he's annotated what Jaeger talked about as being the soda mud flows. They saw them as mud flows. And you'll see as you just run your eye up there, there's the crater varies from being fairly empty to filling up and then emptying again. And that seems to be more or less how this thing functions, as you'll see as we go through the talk. And so here's some important flows that were recognized in the 1960s. And right at the early stage, there's some photographs there from one of Barry Dawson's original publication, showing two types of lava flows. The black, again, being the fresh stuff, very blocky type of lava flows, and others being pohoi, very easily flowing. Now, the significance of this particular eruption was the fact that at that stage, the actual Tanganyika in that time, the Tanzanian Geological Survey, actually had two gentlemen on staff, Barry Dawson and Peter Bowden, who were petrologists. And when these flows happened and were reported, they went up and had a look, climbed down, and actually took some samples of these things and did the first chemical analyses on these so-called mud flows, and recognized at the time that these were actually lavas. And this was very, very important. When they did the geochemistry, they showed that the lavas were very, very high in alkalis, more than 35% combined sodium potassium, with significant calcium, and traced to absent SiO2. So these things were alkaline carbonate rocks. And the principal minerals was solid solution series of sodium, calcium, and alkali carbonates. New minerals that were named from here, Nyrereite after the president of Tanzania, and Gregorite, which was recognized a short time afterwards, named after the Gregory Rift by John Gittins and Dan McKee. So the important thing is that the alkali carbonate minerals are not stable, and they start reacting almost immediately with atmospheric moisture and also with meteoric water, and they'll start degrading almost immediately. In fact, when you climb to the top, if you have a sort of tendency to get the geochemistry of things like I did, you have to take a bag full of silica gel with you and store your samples in that on the way down. Otherwise, they start to deliquesce quite quickly. The important thing is that these lavas are not preserved in the geological record. They decay away and they alter. And I should have pointed out on the map that very close to Oldoinyo L'engai is Lake Natron, and that lake is sodium rich because all the washout waters from the mountain drain straight into there with all these dissolved alkalis. All right, so big news in 1960, the carefully documented thing that these were alkali carbonate lavas were erupting from a volcano in Africa. Well, what was the big import of that? Well, at the time, the carbonatites were suffering a major existential crisis. In the early parts of the 20th century, like granites, carbonatites carbonatites had been described by people working particularly in Scandinavia and then in Africa in the colonial surveys. We're starting to describe these things, which were carbonate bodies that had magmatic-like textures and showed intrusive relationships. And Brugge, in mapping the Fen complex in Norway, first coined the term carbonatite as an intrusive magmatic carbonate rock. This didn't go down well with the experimentalists, because and particularly when it was outspoken on this, that because you could not melt calcite, which it was thought to be the most common at the time, it dissociates at around about 800, 900 degrees. And if you can retain that CO2 and maintain the CO2 overpressure, then it will melt, but it melts at 1310 degrees. And the geological description of these bodies had no major thermal aureoles around them. So this was regarded as unlikely. Many carbonatites are not calcitic, they're dolomitic. And that doesn't help at all because dolomite dissociates about 800 degrees centigrade. So you have the same sort of calcite problem. The other outspoken critic was Shand. In many of his books, quite amusingly, wrote very eloquently about how impossible it was to have a carbonatite magma, which he described as a very strange thing indeed. And just because, and you will know, I did some work on a carbonatite called Spitzkop, and these are his sketches of that's the carbonatite in the middle of Spitzkop, surrounded by alkali silicate rocks. And this is his map that he actually published. And this he saw as a big raft of Melmani dolomite that had been floated up through the Bushveld, and that's all it was. So there's no need, then these were regarded as mobilized or hydrothermally distributed sedimentary limestones. So what's the solution to these sorts of existential crises? Well, granites had sort of got solved by Tuttle and Bone in 1958, classic publication that's been sort of generally described as instant magma, just add water. Put these pictures in because there's an interesting thread that runs through this. This was Tuttle and Bone. Tuttle was worked with Bone at the geophysical lab, and then moved on to his own lab at Penn State, where his postdoc associate was Peter Wiley. And the story goes that after solving the granite, sitting back and thinking about the hoo-ha about carbonatites, he said, well, Peter, why don't you take some calcite and see if you can melt it? And he tried the same trick that they'd used as granites, added water, and succeeded in melting calcite. And the very first paper in the Journal of Petrology, it's a very easy reference to remember, Wiley and Tuttle, 1960, volume 1, page 1. There's the phase diagram, and basically you see that the water is a very effective flux, and so you have calcite plus liquid field going all the way down to just below 700 degrees. So this solves the problem. Carbonatite melts can exist to below 700 degrees centigrade, which that would take away obviously Bowen, but also Shand's objections. The slight problem is that in here, you have this big field of calcite plus CH. CH is calcium hydroxide or portlandite, and portlandite is rare in carbonatites. It's found as an accessory phase in less than 5 localities out of the 572 odd known carbonatite localities around the world. So where were we in 1960? Big year for carbonatites. Lavas had been observed erupting at Oldoinyo L'engai. That proves that carbonatites can exist. Unfortunately, the alkalic compositions are very different from the common calcium and magnesium carbonatites that had been questioned. So it's a bit of a bummer. Secondly, we've got the experiments that prove that calcite will melt. So therefore, intrusive calcite bodies could be carbonatites. Unfortunately, the association with portlandite was not logical. So that's another second problem. So not everybody was persuaded that water was the solution. John Gittins, who has the thread again, was one of Frank Tuttle's team at Penn State. John always kept a very strong eye on field relationships and went out to the field all the time. So he always constrained his experiments by what he saw in nature. And he always felt that fluorine was worth trying. fluorine is found associated with carbonatites. You get fluorite deposits related with Ambadonga and in Namibia as well. And in '64, he published a paper with Frank Tuttle showing the effectiveness of fluorine as a flux in carbonatites. Then in response partly to trying to solve how the Lengai lava is formed, Alan Cooper joined him on a postdoc type sabbatical study and did some experiments using alkalis. Just for interest, John Gittins in his entire career at U of T only ever had two postdocs or sabbatical students, one Cooper and the other one was me. And then also with the fluorine, he kept on and looked at the effect of alkalis plus fluorine. Beckett was a research student of his, and he did the same thing with alkalis in the dolomite system. The Cooper and Gittins and Tuttle paper is on calcite. So these are what those phase diagrams look like, and you'll see this is with sodium carbonate and potassium carbonate. Very strong fluxing. Again, here we get liquid carbonatites down to 800 odd degrees, nicely geologically reasonable, and you crystallize calcite plus liquid, and your accessory phases, the alkali here is nararite, which is found in natural, obviously the Lengai carbonatites. On the right here is the Jago and Gittins paper, where, so this here is effectively that diagram, just with varying degrees of fluorine added to it. And you see that fluorine adds to the effectiveness. And so a combination of alkalis plus fluorine will get the final liquids down to about 600 degrees centigrade. So this is all good news. One of the problems is that this system has a eutectic down there. So what that means is that's a minimum temperature. And so you can get these liquids on this side, okay, here, what that creates is a thermal barrier, if you like. And so if you're on the calcite-rich side of this mix, then that's fine. You can produce the calcitic carbonatites that we find in the field, and the same system works exactly the same way in dolomites. So you can generate your dolomites, but you can't drive this past this to produce your Lengai lavas. So this led to the concept that, you know, the Lengai was different to the rest. In other words, these weren't residues. I think most people who'd worked on carbonatites felt that probably the easiest interpretation of what Lengai was is that it was the residual melt from normal carbonatites crystallizing at depth. But not everyone agreed with that, and otherwise intelligent people sort of went off and developed alternative theories. Mike Labar, who had massive amounts of experience mapping, he and his students mapping carbonatites on the eastern shores of Lake Victoria, and published very, very good field reports on these in a book. In '81, proposed that, in fact, all carbonatites, the calcium and dolomitic ones, were derived from alkalic parental magmas. These alkalic parental magmas were derived by liquid immiscibility from nephrolitic or phonolytic starting things. There was experimental data showing this, and the immiscible carbonate liquid was alkali rich. And then he came up with a system whereby the alkalis get lost into phenatization. Phenatization is the name given to alkali metasomatism that's characteristic around most carbonatite intrusions. And the phenatization derives from this first being described by Brugger around the Fen complex. And then, so the phenatization takes away the alkalis, and then you go from these residual things through from calcite carbonatite through to magnesium carbonatite by fractional crystallization. That was the model. Jim Twyman, a student of John Gittins, they didn't like this idea at all, didn't think it worked. And they just simply took some carbonatites that had alkali silicate minerals, accessory minerals in it, and just had a look and probed core to rim compositions in the accessory minerals, and that's what's plotted here. So the arrows are showing cores to rims, and you'll see that core to rim, the alkalis increase in composition. So it's the opposite direction to what Mike DeBar said would happen. And that sort of put to rest, I think, thankfully, that model. But Barry Dawson, there was a well-known xenolith of calcitic lava, a block of calcite carbonatite, in other words, in the nitric carbonatites at Lengai. And Dawson argued that basically that this was cervite is just an old name for calcite carbonatite. On textural, mineralogical, and stable isotope grounds, is now reinterpreted as a highly altered nitric carbonatite lava. Again, some of us didn't really agree with this too much. What is required through that process would be to replace take nirariite, which is soda calcium. You'll see there's mole of sodium oxide for mole of calcium oxide. Convert that to to just calcite, massive volume difference, and create crystals that were actually near perfect pseudomorphs. There was other evidence put together on this as well, and so felt that this is ludicrous. And there were more than this. I'm not just on the blame Dawson on this one. A lot of people were interpreting little microphenocrysts, perfectly crystalline microphenocrysts of calcite and complexes like Kaiserstuhl as replaced alkali carbonates. And then the cherry on the top is for Daniel Weidendorfer and co-authors did experimental work on, like the Cooper et al. Studies, but used actual Lengai lavas. And what they found is when you use these natural compositions where you've got sodium and potassium together in the system, that eutectic disappears. And so these compositions up here can slide right down through that point to effectively come to a eutectic that is very much like the Lengai lavas. So based on this experimental stuff, there's no barrier between the natural calcitic magnesium carbonatites and the Lengai residues. All right, so those are the major, I think, influences on carbonatite thinking. I'd just like to put a personal one in as at the end off now. So if we look at post-1960, this is going from here where Barry Dawson and did the sampling and whatever. Okay, here you see that the cone is filled up with ash. It filled up with a Plinian eruption in 1966. And then that ended about in 83. And in 1988 here, you've got an open crater with lavas flowing in that. Okay, so just to focus in on those two types of flows, you see this is a picture I took on the 95 trip. These are old flows, and you'll see there's the hammer for scale. These things are very, very thin, and they're very, very low viscosity lavas. There's some classic movies, I'm not sure if they're still accessible, from the Killers, not the Killers, Kraft. Mr. and Mrs. Kraft, both volcanologists who made movies for National Geographic, and they showed pictures of the actual lava flows, actual live lava flows from Lengai, and these things just are very, very fluent. So this is a typical Pohoihoi type of flow, but then throughout the history, they also have erupted these eye or blocky types of flows. And in Barry Dawson's study of colleagues of that with Barry Dawson, published in '95, just did a sort of petrographic analysis of these highly mobile versus the viscous, blocky R-type flows. And you'll see that the major difference is the large amount of large phenocrysts. And if you look at the ground mass, these have got very low volumes of ground mass material. Now, the reason that material with large amount of crystals, normally in a silicate magma that would make it very, very difficult to move, the big thing that's different in carbonatites is the fact that they have an incredibly low viscosity. As the diagram on the right there shows, about more than 2 orders of magnitude less viscous than a basalt at its liquidus. So if you visualize the flows that you see every time the Hawaiian volcanoes sort of spew out lava, how low viscosity those basalts look, these carbonatites are 2 orders of magnitude less viscous than those. Okay, so let's move on to the trip that I was on in '95, that climbed to the top of the Lengai. This was associated with the African Geology Conference in Nairobi that year, which, interestingly enough, was the first time that the African Geology Conference had ever been held in Africa. So go figure. But because of this, there was also an IGCP project on carbonatites during those years. So we used that as an excuse to set up a trip here. And so when we climbed up to the top, that's what the crater looked like from the top. This spur here, just put that in your mind, because it's quite a nice marker in some of the stuff I'll show you later. We found a bunch of these hornitos. You can see little bits and pieces splattering out. When we were in the crater, you could hear the magmas at depth bubbling over. The fact that they're below your feet for some reason doesn't bug you. But so we were sitting watching this, and just for people in the know, that's Francis Wall, who now heads up Camborne School of Mines. That's Roger Mitchell. And this here's Louis Skurman. He's a carbonatite guy in Australia. And we sat watching this for quite a while. And then what happened was a lava lake just behind you that we had a look at, but it was popping things out like that, so it was a bit dangerous. The edge breached. And that arrow there is just to locate between this hornito and that white one. You can see this is the one we were looking at here, and that's that white collar. So it broke through the back, and one of these blocky lavas poured out. And we were able to walk next to it as it flowed out very slowly. You could actually see the sun reflecting off the crystals that you could see in the actual moving lava, and you could hear a crunching sound that of the crystals rubbing against each other. So once it had slowed down, you could actually take some samples of it. So that's me there taking my most accurately dated sample ever, 11:30, 17th of October, plus or minus 15 minutes. The inaccuracy is not analytical, it's just I didn't look at my watch. And then your killer was along on the trip as well, and being a good German, he had a barometer with him and was able to measure the temperature at around about 530 degrees. So low temperature, we watched this thing flowing. And the sample I took and sectioned when I got back, that's what it looked like. These are vesicles in here, but these are Gregorite and Narreriite primocrysts, and you can see the dark material in between is the interstitial material. These primocrysts over 90% by volume, and we watched this thing flow for at least 40 to 50 meters, and it didn't pile up on itself. So that gives you a nice visual indication that carbonatites can intrude with a large crystal load. Much of my work on carbonatites has been involved with predominantly dolomitic carbonatites in the central part of the Carbonates craton, plus minus 1.4. And some work I've been focused on doing off and on for years, but being focused on more recently, are these 3 intrusions, which are lumped together as called the Bullock intrusions. That's Pilanesberg as your marker. Just go through this quite quickly. This is for Wood's, an interpretation of a Wood's sketch map. These blue stuff here are the intrusive dolomites, and each of these centers intrusive dolomitic carbonatite intruding into the Bushveld granites, phenatizing the Bushveld granites, and the intrusions are pulsed. You can separate 3 distinct phases of intrusion. The first one had a high gas pressure, hydraulically fractured the granites, broke its way through, and choked with large amounts of clasts of granite. The next phase, the important thing here to separate it from, say, a granite system with water as the flux, that hydraulic overpressure was not the actual flux. It didn't relieve the flux. The next intrusion was a liquid, easily flowable injection. And you can see here the crystals are flow aligned. These quite large crystals there, and you can see there's an internal contact. These are multiply intruded. Now, hope you can see this. This is the foliation, the flow foliation, and you can see it's actually bending itself around this interference, okay? And here there's, again, same sort of thing. These are clearly phenocrysts that are in this lava, in the magma, sorry, intruding, and you're getting some sort of drag on the sides, and you're getting a beautifully formed flow fold. Here are some xenoliths with almost like a strain shadow type of approach. The flow, flowing around here is aligning these things. Foliations like this in carbonatites are ubiquitous, and they generally subvertical, and so these require the fact that these carbonatites can't intrude as liquids; they must intrude as crystal mushes. So this is what these things look like in thin section, very rhombic. Under the microscope, they're interesting, but they become particularly interesting under the SEM. Now, the dolomites are solid solutions with progressive substitutions of iron for the magnesium with falling temperature. And so the difference in atomic number between iron and magnesium means that the backscatter electron imaging, SEM, shows this up absolutely beautifully. So what we're looking at here are 2 different samples, and the light colors here are the rims, the dark here are the big ROMs, and you can see there's virtually no variation in iron to magnesium ratio here. So these were flowing in the magma, in contact with lots of magma, so therefore they didn't show any zoning. It's only once that stops that here we have is the trapped interstitial liquid that very quickly changes in composition, okay? And you can see between there, the ROMs make up probably over 90%. Where you have, these are finer grain things, and this is sort of thing repeated. These would be finer, slightly more elongate ROMs. You can see the scale bar here, they're much finer grained, but the same sort of thing. You have a lot of crystals that are flowing in the magma. I won't worry about that. So effectively, this would be very difficult to persuade colleagues that this can actually happen with this crystal load if it wasn't for actually Lengai being able to see that and flowing past you. It actually gives you confidence in interpreting this lot. So I want to go into this. This is another field that I'm busy with at the moment. But okay, so after 95, there's a lot of information on Lengai. It's become a bit of an adventure destination. And there are various people through the years that have acted as post people, where people submit their reports of what they saw when they're out there. So there's a huge web source of information. So here's some photographs from 2003, 2004. You can see these are the hornitos. The fact that they're actually light colored and white means that they're old. That one there might still be active, but these aren't. And all these flows here have been around for quite a while. You'll see they've all degraded. Here's a photograph taken at night, 2004, with fresh lava glowing nicely in the dark. Post 95, you can see here, these light streaks here are actually lava flows that have overlapped the crater. So if you remember the picture I showed you, we was looking down, there was quite a drop down to the base of the crater with that pointy point sticking up over here. So you can see around about 2006, 2007, the crater was completely full. Here is fresh lava spewing out, and these are old flows that have overlooked the edge. Obviously, from around this time, they stopped any things of ascending to the top. And then in 2007, again, we had Plinian eruptions from Lengai. Barry Dawson obviously had a look at it as well. This is a picture that he's posted. A few other going through to October, so from September, October 2007. There's that point that I said to look at from the 95 trip, and you'll see this whole area is filled up now. So meters and meters above where we saw it in 95. Some interesting pics. This one here is a photograph taken by the KLM aircrew of an international flight coming past. So you almost eyeball to eyeball here. So you're about, the top of that thing is about at the cruising height of these international flights. And this was from another plane. I didn't note down which flight it was from Johannesburg to Nairobi, but they estimated that this would have been taken from the plane, that the top of that must have been about 50,000 feet. It's quite a dramatic picture by this guy, Drummond Murray. He posted a YouTube video, and I just did a clip of this. This is Lengai under there, that big, very, very active cloud. And it was taken from a place called Ngarasero, which is a little camp that when you go up there, you stay there. When we were at the camp, we had the sort of headman around for a beer with us around the fire. And we asked him what Ngarasero meant. And took a while, and we worked out that it effectively meant where the cars park. So it sounded very romantic, but wasn't. And that's a sort of recent picture from this volcano discovery of, this is the point that I was talking about, guy sitting at the top looking down into the crater. So you can't even see any of those crater walls that we saw back in 95. And that's Lake Natron in the back. Okay, thanks.
Thanks, Jock. Okay, let's unshare your pictures and then throw it open to questions.
There's a first question from Andy Clay that says, "Hi, Jock, where does the Lengai magma develop in the mantle, and is there any linkage to kimberlite?"
Well, there's a linkage to kimberlite. You're talking. This is a 3 2-hour talks, Andy. But I think the most clear link between carbonatites and kimberlites is that they develop in the mantle. And interpreting some of the isotopic stuff, they come from more or less the same part of the mantle. I think the big difference is what happens subsequent to where they are generated. Carbonatites are low degree melts of the mantle. Otherwise, as soon as you increase the degree of melting, you get more alkalic components going in. So I think those are the things that I believe that carbonatites are primary melts of the mantle and can get to the surface like other people don't. They want to use immiscibility, which I don't believe in. But so I think there aren't obvious direct links apart from the degree of melting between the two. And I think kimberlites are generated at significantly greater depths probably, but it's all about how they get to surface.
Okay, someone else had their hands up. Yeah, well, Lou's hit the question on the head too. Lou, do you want to ask your question and get that debate going? Is it lithosphere or mantle? And again, Jock, I mean, surely the structural setting seems to also play a role.
Yeah,
I'm just curious because there seems to be a polarity of opinion about carbonatite sources and a similar one for kimberlite sources. So what's your view?
Yeah, I think, I don't know, tried very hard in a couple of papers we've published to point out what how these things work, that there's data. And if you Lou, in your recent talk, you talked about the new Anexi picrites and whatever, and we published a paper way back when, looking at the isotopic composition of the carbonatites in in Zim, because we knew there was that funny enriched mantle, subcontinental mantle. So it was a useful test to go and say, well, what do the carbonatites see that? Where are they coming from? And around the carbonatites, they're associated with nephronites. We did the isotopes on that. Those nephronites have the same sort of range of extreme compositions that the picrites have, and the carbonatites don't. But one of the carbonatites showed some enrichment. So in other words, that is, to me, a fairly powerful thing, that the source of the carbonatite material was generated from lower than where that enriched subcontinental mantle was, okay? Because the one picked up on it on its way through, if you see what I'm getting at. It doesn't have to be in the asthenosphere, but, you know, I think the key answer to that debate is if you look at the melting conditions, the PT stuff for carbonatite melts, it sits below what they call the ledge, you know, where there's a big excursion in the melting curve around about 75 to 80 kilometers. And that, I think, plays a big role in getting carbonatites to the surface. It's a collecting point. So, you know, carbonatites can be generated way down hundreds of kilometers, but no matter how they get, if they stay in equilibrium with the mantle, they'll cross that little barrier, which is not they don't get quenched, they actually interact and react with that. So, you know, it's both. I don't think it's either or. You know, that's if you're talking asthenosphere or subcontinental mantle. You get carbonatites coming through thick mantles that do not have any isotopic signal that you don't find in oceanic basalts. That to me is a pretty strong signal.
Thank you. Lutendo Mavungu has a question for you. Lutendo, if you can unmute yourself, come on camera.
Hi, everyone. Sorry, I think I just raised that hand by mistake. Sorry, I didn't see that typo.
Well, you're going to have to ask a question now.
Thank you, Jack. I really appreciate the talk. Good.
Okay, Neil Phillips, you've got there, Danny.
Yes. Neil?
First of all, Jock, a really interesting talk, great summary and wonderfully illustrated. I've learned an awful lot, so thank you. You talked about quite a lot of volcanoes around there, and you only mentioned one other was a carbonatite. What about all the rest that are in the like 5 or 10 kilometre sort of vicinity of ODL? Are they all different?
There are quite a few around. There's another one just on the border with Kenya. Names this one, but it was quite a famous one. Bruce Kersgaard, I think, did some work on it. There are a number around. They cluster in that Rift Valley area, but there's a lot of other magmatism. I mean, the carbonatites are preceded by sort of outpourings of phonolytic platophonolites and nephronites and whatever. And before and after, there's a lot of active little fumaroles around and that sort of thing.
Okay, I think it's those ones I'm probably referring to that are fairly close and very clearly non-carbonatite in nature. Basically, you're saying they're from a different part of the mantle and earlier or later, that sort of thing. Well,
it's all down to the amount of CO2 that's there, if you think about it. Like, for example, the carbonatites come through and they develop and can get to the surface when the carbonate, the CO2 that's there is concentrated in enough of a volume for them to collect and come up to the surface. If the melting goes further on, you start generating sort of nephronites and melilitites and nephronites and whatever. Okay, so those then will erupt, and volumetrically those are higher degree melts, and you find more of them at the surface. So I think there's something like 570 odd carbonatites known worldwide. Yep. And if you compare that to sort of the there are more than way more than 1,000 kimberlites in the carbonate craton alone. So, you know, it's more difficult for carbonatites to get to surface than, say, something like a kimberlite, and that's why I think they're less. And
okay, yeah, no, understood that. Thank you.
Could I ask a question, John and Jock?
Yeah, sure, go for it, Richard. Yeah.
Thanks very much for that very interesting talk. I just wanted to ask you, how does the Pilanesberg fit into this story? You know, it's got a couple of intriguing things. Number one, are the intrusion of kimberlites right into that same volcanic vent as the Pilanesberg? Number two, characterized by fluorite deposits in more than I'd realized. In fact, I've just got back from the Pilanesberg and try to have a re-look at it, but it's a bit difficult doing a field traverse now. But nevertheless, it looks intriguing in terms of what you've just said. So how do you see it fitting into the carbonatite story and the kimberlite story for that matter?
how many hours you got?
Plenty.
Yeah, look, the alkali, the fluorine there is typical of that type of, you know, there's cyanides associated with some of the carbonatites of that 1.4 age, but none of them have the composition of the Pilanesberg, these so-called agpietic, very high trace element concentrations. And those sorts of rocks tend to hunt together with carbonatites, you know, so much so that, you know, the prevalent argument is that carbonatites are the immiscible fraction from the fractionation of those sorts of things rather than primary magmas on the own. I've always fought against that because in the number of things that I've studied, that doesn't work with the isotopic relationships. So you know, there's no obvious direct association, but the fact that they are there together is not unusual. The kimberlite there is much younger, you know, so it's intruded much later. And you know, the thing is, the things like carbonatites and kimberlites are going to make use of any weakness or any easy way of getting to surface. So the Pilanesberg had pummeled its way through these flat-lying, you know, subhorizontal layered rocks of the Bushveld and the granites. So, you know, I don't think it's unusual that it's come up there because there would be an interface, a sort of structure, probably a weakness along there. And then you've got those post-Bushveld the dike swarm there that goes up parallel to the sort of Russenberg limb of the Bushveld would also be fractures, and that's probably why the Pilanesberg is sited where it is. The direct petrological association, you know, needs more work to work its way through that. If you read the arguments in the literature, you know, a lot of people like liquid immiscibility, that you start up with a carbonated silicate volcanic, but the work that I've done shows that it can't be the case in many cases. In other words, there's a whole bunch of white crows out there that I've seen. And so why use it if it doesn't work for Spitzkop, if it doesn't work for the Zimbabwean ones, if it doesn't work for most of the ones that we looked at in South Africa, then why do you need liquid immiscibility doesn't work, and it's more logical just to take that these things can come out from the mantle. So that's my viewpoint. Now, on the way up, the carbonatite, if it actually doesn't get to the surface, will interact and metasomatize any of the rocks that it's in contact with. And if I talked about phennites, these alkali metasomatized rims around the carbonatites. If you take those things and plot them on the petrogeny, the 5-phase diagram, they spread all the way from the granite minimum through to the nepheline cyanide minimum. In other words, if you take this and pump heat into them, they will melt as coexisting nepheline cyanides and quartz cyanides in the same complex. So, you know, the carbonatite could be the precursors to the
Yeah.
alkaline rocks. Take a carbonatite, mix it with a crustal granite, then you've got the perfect starting material for a cyanide, nepheline cyanide thing.
Okay, interesting.
Doesn't really
Thank you
answer
for
it. It's a long story.
Jock, there's an associated question in the text, but my English is not good enough for that. You want to read that in the text column?
Under the chats.
Some of the names are unpronounceable for me.
Which
From
one is
J
it?
Monroe. J Monroe, it says, "Hi, thanks for the great talk.
The
If
miscibility
immiscibility
doesn't
is
involve how do we get common carbonatite phosphorite associations with similar radiogenic isotope ranges and interbedded magmas? Well, in the Slavonian carbonatite phosphorite associations, those things have got such extreme crustal isotopic signatures that you know, they aren't normal mantle rocks. And the difference with the phosphorite association is largely to do with how much silica is in the starting magma. If you have high silica, in other words, a carbonatite, a silico-carbonatite with high silica, then the high temperature mineral phases that will crystallize from that will be magnesium silicates, there'll be olivines, there'll be clinopyroxenes and those sorts of things. If there isn't silica, then the high temperature mineral that crystallizes out is calcite, because dolomite dissociates, it's incongruently melting. So the high temperature phase in a carbonatite without a lot of silicates is calcite, and only below 800 degrees will dolomite start to crystallize. And that's a really important distinction that people are missing. Phosphorites are always calcite related, okay? And I think they're starting it with a different composition to normal ones. And the association between finding carbonatites cheek by jowl with alkaline silicate rocks is common, but there's more than 100 cases out of the 500 that are in the database that are carbonatites alone. So you need to explain those, you know.
Mickey.
Sorry?
That's the dog.
Sorry, it was me shouting at the dog.
I thought I was being told to shut up or something. It wouldn't be the first time. Yeah, and so my PhD that I did with, you know, on Spitzkorp has peroxenites, igelites, nepheline cyanides, and the last phase is carbonatite, the perfect so-called association. And if you do the isotopes on that, the carbonatite is mantle-like, and the others have more evolved crustal signatures. You can't derive the carbonatite from those because it's got different isotopic ratios. At the point of immiscibility, the isotopic ratios, or all things, will be in equilibrium between the carbonate phase and the silicate phase. So you'd expect them to have exactly the same isotopic signature. Okay, so that's why I argued for that, and John Gittins and myself published the JPET paper where we argued for a mantle origin for carbonatites based on differences, small differences between the silicate rocks and the alkali and the carbonatite rocks in Rift Valley complexes. Okay, so I don't know if that answers your question, but it's, you know, it's don't forget, if you'll only get a different isotopic composition if there's something different in the environment to change it. If you don't have a metasomatized mantle, old metasomatized mantle with unusual isotopic things, then carbonatites and silicate rocks will have the same isotopic composition. The fact that they have the same doesn't mean that they're linked by immiscibility. But if they're different, it means they definitely can't be. Hope that.
Okay. John Simona says, thanks for a great presentation. Isn't it time for another visit to OL, as the last photo was taken in 2017?
That's the last one I put up, yeah.
Yeah, so we're organizing the OGG group to go there next, Kenny, you leading the way.
Okay.
And if I can just come back there, Jock, I mean, you know, your start of the presentation just highlights how convoluted and back and forth this whole argument has gone. And, you know, I certainly would agree. I mean, it's quite difficult to look at all this with liquid immiscibility. But if we start in the Northern Lubombo, and obviously Nuanetsi is, to me, a really good example. Surely, and then look at Lengai, and I go back to Neil's questions. If you go back to Lengai, I mean, the true carbonatite magmas are two in a field of many more volcanoes. And they actually, you know, look to me as a simple petrologist like the initial, you know, smallest partial melt out of that sort of whole volcanic field. And it's associated with the rift. So aren't we perhaps just looking at sort of the early, it doesn't necessarily have to be early, but the very early, very tiny partial melts, you know, with fluorine and whatever other volatiles we need to kick off those just amazing melts and, you know, amazing lava flows and that volcano. And then with the progression of time, and, you know, it's exactly what we see in the Lubombo, or the Lubombo and Nuanetsi, the actual carbonatites are volumetrically very small. And if you look at many of those so-called carbonatites in Nuanetsi, there's an awful lot of stuff that, to me, actually looks like, you know, rather more silicious rocks which have been extensively carbonatized or phenotized or altered, whichever way you want to call it. Because if you come across to the Northern Lubombo and Kruger Park, I mean, you see little signs here and there of a bit of carbonatic material, and then you get some lovely nephlenites, but they are, you know, volumetrically very small compared to the then massive outpouring of initially pickrite basalts with all the stewed up chemistry, and then, you know, the voluminous ordinary basalts. And you know, as I say, in the interest of keeping it simple, I would tend to agree. So they're not immiscible, but then they're very small initial tiny partial melts of which is obviously going to pick up all the stewy stuff, you know. And it's the same if you go back to the Pilanesberg. I mean, the real carbonatitic stuff there is actually very small, you know, once you look through the phenotization and the alteration.
Well, there's no carbonatite in Pilanesberg at all.
Yeah, sure. It's just all altered material.
No, it's not. I mean, you know, Bullock is just down the road, and that's an intrusive thing on its own. So the fact that you use the term carbonated, I like very much, because what happened at a time, anything that was carbonated around was called carbonatized. Yeah. Giving the feeling that it's actually carbonatites are magmatic rocks, so therefore that's an oxymoron. The thing at Lengai, the soda carbonates that are coming out are not the only carbonatites there. Yeah. You know, that whole volcano is a silicious volcano, but it's erupted carbonatites with the silicate rocks through time. And because of the xenoliths coming up, when that thing erodes down, there'll be a calcite carbonatite plug further down. So it's rather than it being it's not, you're looking at the wrongs, it's not the early low degree melts. What you're looking at there is the distillates of all the other stuff crystallizing out. And what you're seeing there is the flux component now being concentrated and coming out. And that's what, you know, Weidendorf's, Daniel's sort of work allows us to say. Yeah.
But inherently it's still carbonatitic, or it's still a primary magma, let's call it that. So, you know, whether you're looking at the distillate or the portion that's lower down, it's still what you would call it, you know, a carbonatite.
No, it is a carbonatite.
Yeah.
And the thing is that what I didn't go into with the research I'm doing on these dolomitic rocks, I mean, anyone who is looking closely at those backscatter images, you'll see that the interstitial phase in amongst those ROMs is quartz. Yeah. It's fine-grained cherty quartz. Yeah. I've got some slides there where they're perfect pseudomorphs after a previous phase. And what that is in fact the crystallization of the nirurites, probably 2% in the interstitial stuff that's been taken out by the groundwater, and the silica is filled in between. So what you're seeing there is that, you know, it's crystallizing in situ. But, and so, you know, you're looking at the mass balance at Lengai, these alkaline things, or just the flux, because the flux will, you know, it's not like there's no second boiling in that system. So it just concentrates all the time. It becomes less and less viscous, so it can move out. And what you're seeing there is that just being ejected. And so it's giving you a little time slice of, if we put 4 or 5 million years on the top of the road off, and you'll be down into the other carbonatites, surrounded by nephronites and phonolites and whatnot.
Yeah, but that's my point. You know, there's a classic carbonatite, and even, you know, when you go down, obviously there's still some silica in it, but then all the other rocks are somewhat more mafic rocks, the sort of higher degree partial melts. I'm just trying to, you know, look at it in a very simple context.
If you go to the JPET paper in '98 that John and I wrote, what we did there is to say, okay, if these things were miscible, then, you know, they talk about it, you know, a fractionating silicate rock that gets to a stage when carbonate reaches saturation, and that's when you get immiscibility. And if you look at it, the point of contact in the isotopes between the carbonatites and the silicate rocks, they only overlap with the most primitive of the rocks, not the evolved ones, all the time. So that doesn't fit that sort of story. I think the big thing is that carbonatite melts will be out of equilibrium with virtually any surroundings from 75 kilometers to the surface.
Yeah,
we find them at the surface, so they need special help. That's why you find them in rift valleys and stuff like that.
Yeah, sure. And I'm, you know, I'm not arguing about the miscibility. I'm rather going back to, you know, partial melting, very small and somewhat higher.
Yeah, well, if you just think about the, you know, as the geotherm's crossing the liquidus, you know, you're going to go out, you're going to melt it's you know, if you go out and melt things up to millilitites or nephronites, at some stage that thing is going to start cooling. As it comes back down, if there's any CO2 left, you know, you will be generating carbonatite melts. So those are the things to just think about. You know, I can give a talk on this, but I've been through that, and I think very, very much that big inflection in the peridotite CO2 melting is very, very important in thinking about carbonatites. I think it acts as a collector, allows the melts to get up, collect together. These are very, very low viscosity. They separate from the matrix when they're melting at something like 0.01% partial melt. Yeah. Okay, which is very easy to move them. But that means, how do you create a pocket of magma? You don't. You can't. They're going to just, you know, the biggest story.
There is no magma. Okay. Right. Other questions?
Jock, we've got Gillian in the text chat column again. She's also attached a document for you to have a look at. If you can just see it, would be can you see what she says? I would be interested in the colleague's opinion on this. Always thought the East African rift carbonates were crustal in origin, and I'm surprised to hear colleagues with quite deep mental ideas.
Yeah, I'm not saying deep mantle, but certainly the melting. I mean, if you go back into the would be the middle to late 80s, early 90s, there were quite a few publications of melt studies, not on artificial CMAS type systems, but on actual peridotites and actual eclogites with CO2. And if you look at the melts generated by those, they are dolomitic carbonatite melts with, depending on how much alkalis they were, how fertile the peridotites are, then there'll be alkalis in those melts. So therefore that you've got your flux and everything, and those will you know, can move on. So I don't know how you can generate carbonatites in the crust. Firstly, petrologically, and secondly, it doesn't explain the overriding. Most carbonatites have neodymium strontium ratios that are exactly. The best way of putting it is if you compile the data, there's no components in the range that you don't find in oceanic basalts, ocean island basalts and mid-ocean ridge basalts. That means even though they come and intrude into continents, there's no component that you can identify as going into them from the continent. I mean, that's been accepted since for quite a long time. So there can be other components, but essentially these things must come from the mantle. Even the miscibilists say that, you know, the carbonatite might be created at a crustal depth, but it's coming from a mantle melt.
Yeah, I would tend to agree. I mean, I think the general consensus is that, you know, these rocks come from the mantle, and I think the important thing, Jock, and we've touched on it a bit, is distinguishing between the real carbonatites, which you've talked about, and all these other carbonatized rocks. And I think that's also part of our confusion in this picture. So my question is, what have you been doing in Germany, and what's next out of this story?
Well, what I've been doing is actually doing just laser probing of the zonings.
Okay.
You know, to look at, you can see the major element things, and it was just to say, well, what sort of trace element changes are we depicting? Not the examples I showed you where there's more zoning and you get interstitial. You can essentially see the magma dying out. So the idea is to try and constrain how effective magmatic fractional crystallization is in starting rare earths, enriching rare earths, okay, prior to getting into hydrothermal changes and stuff. And from the initial data, we've got you get an order of magnitude change or more in the rare earth concentrations from core to rim and those goodies. So it's very effective.
So we look forward to that. And then just the last question, obviously we had some economic geologists or people interested in economic aspects. I mean, what's the difference between, you know, carbonatites that have economic value and rare earths compared to, you know, some of those that don't? I mean, is there any particular, you know, aspect that distinguishes carbonatites and commoditites, or does it get back to this, they're real carbonatites and then they're carbonatized, you know, alkalic rocks?
Look, you've got to be be careful of that, and it's very significant. If you read about the Lofdal project or rare earth thing, it's very, very important there, because initially Francis Wall published a paper trying to come up with ways that you could get these heavy rare earth enriched carbonatite dikes. And with the resource work that they've been doing now, I mean, the guys that Scott Swindon that worked on and Pete Seafried that worked on it showed that there were two types of these so-called regional dikes. One were carbonatites and the other were carbonate alteration zones. And it's the carbonate
just for the audience,
alteration.
just for the audience, Jock, which ones are you talking about?
This is at Lofdal. It's a deposit in Namibia.
Yeah.
And it's associated with there's a couple of carbonatite plugs, and this well, I don't want to get into that, but these are now competent persons going and doing a study and a report. They're not thinking about theories or whatever, they're just describing what's there. And they picked up the fact that the ones that are carrying the high heavy rare earth concentrations are in fact replacement things. And so they're not magmatic. If you look at the other ones, and then they have exactly the same rare earth profiles as these plugs of carbonatite that are similar to most carbonatites. Most carbonatites have light rare earth enriched rare earth patterns. Okay, so short answer to the exploration things. If you want to find rare earths in carbonatites, don't go looking in phosphorites, don't go looking in calcite carbonatites. If you've got mixed compositions, the magnesian ones, the dolomitic ones are low temperature, and the higher the iron is, the lower the temperature is, and those are the ones where you tend to find the highest rare earths. So.
Okay, well, that's great. I mean, it goes back to doing, good field geology, good petrography, and knowing your rocks again. It's like kimberlites. They're kimberlites and kimberlites.
Yeah.
Well, John, there's been growing support from the audience for this field trip that you are posing. So let's get the names and let's get the funding and let's get out there.
Well, you organizing it, Henny, so that's your game. Okay, right. Thanks, Jock. That was fantastic and really good to have these different views. But I think
the dog thinks it's good too, Jock.
yeah. Sorry about my dog in the background. But anyway, Jock, I mean, I think this topic will not sort of die lightly. So by the time you've finished your work and interpretation of all the stuff in Germany, we'll need a new presentation or further presentation next year. Okay. Fantastic. Thanks very much. I'd also like to just say to everyone, we're in the process of planning next year's presentations. I mean, hopefully next year.